Hello and welcome to my channel. Today I'm going to be testing out these two antennas with gain, directional antennas for Meshtastic, 868 MHz ISM band. First one is this McGill Microwave Systems 10 dBi flat panel antenna, which is quite thin. It's actually maybe just less than an inch. Look at that. And on the back there's an end connector with some adapters and some thin cable. The type number is written there. So it's 868 MHz 10 dBi basically. And the other antenna is the one I already tested a little bit, which is this Paradar 12 dpi 8 element Yagi. I'm just going to compare the performance indoors, which is not a very fair test. It should be done on an antenna test range in an anechoic chamber, all the things I don't have. What I do have though is a long corridor, which I'm going to use as my test range. In order to measure or compare the output from the antennas, it's nice to be in the far field of the antennas, not the near field. And the far field starts at around 5 wavelengths, and we're at almost 1 gigahertz, which is a wavelength of 30 centimeters. And so 5 times that is 1.5 meters. And my corridor here to the end where the door is about 8 meters, so it should be well into the far field of these antennas. We don't want to test in the near field. That's really not fair for trying to measure performance. And to be able to do this measurement, I'm going to use the test equipment which I have, which is this cheap, very inexpensive vector network analyzer, which is the Nano VNA, which I've got transmitting at 869 megahertz focus, and it's set to 0 sweep because it's really a sweep generator normally for making network measurements, but in this case I've just put an antenna on it, one of these little helical stubby antennas, and 0 sweep, so it's transmitting a plain carrier at 869 megahertz. It won't go too far because the signal level I think is about -17 or -20 dBm, and it's inside an apartment with concrete walls that are reinforced with steel, so probably nothing much is getting radiated outside. And for the receiving side, I'm going to use a tiny SA network analyzer. At the moment it has the same antenna on it, and this is measuring at 869 megahertz, and you can see current signal level is about -30 dBm because these are right next to each other. So what I'm going to do is I'm going to take the transmitting device, take it down the antenna test range, put it into my standard antenna holder, which is this boot or shoe if you're listening in German. That goes there. So that's sending out the signal at 869 megahertz carrier, and then go back down the test range. I'm going to move these antennas out of the way a little bit because of course there's going to be a lot of interaction between all this metal, and these are resonant at 868. Of course there are going to be a lot of reflections inside this building, which will cause multi-path effects, which will affect the signal strength, producing dips and peaks in the signal, which is all very nasty, but that's the best I can do. So I've got -60 dBm there. What I'm going to do is just move around a little bit in case there are some cancellations and multipath effects, and just look at the maximum I can get, which seems to be -60. Remember, lower numbers are higher signal levels. I'm trying to stay level with the edge of the table to keep the distance the same. So it looks like it's about -60 dBm being received at the maximum. So that's the little stubby antenna. What I'm going to do now, sorry about the wobbles, I did get a selfie stick, but I'm going to put this antenna at the edge of the table, so in the same spot, and then I'm going to connect it to the receiver spectrum analyzer, measure the signal level, and again I'm going to move the antenna around to try to find the peak. So you can't see, but I'm actually connecting the coax now to the network analyzer receiver. So there we are, there's the antenna, there's the coax connected to the Nano VNA, and I've got -54 dBm. Let's try to move that around. Now you're not going to be able to see as I do this, sorry about this, I've only got 2 hands. So I'm going to move the antenna around to get the best possible signal strength, and up and down a bit, why not? Now it looks like the best I can get is -53.9 or so. That's about the strongest signal, minus 53. They call it minus 54 dBm, being received by the flat panel antenna. And with the little stubby antenna, I was getting minus 60 dBm. So the difference in signal level is 6 dBs, which is a factor of 4 in power. So 6 dBs. It doesn't mean that this has a gain of 6 dBi, this flat panel, because the little stubby antenna has a gain of 2 dBi. So you can work out what the gain is. But the signal level has increased by 6 dBs, and so that means the actual gain roughly is about 8 dBi over an isotropic radiator. So it's 8 dBs, which is not bad, fairly close to the claimed value of 10, but this is certainly not a fair measurement, and I'm not complaining about it. 8 dBs in this test setup is great. So I'm going to now turn around this antenna rig so that the beam is pointing down the test range and connect it to the analyzer. So sorry you can't see what I'm doing while I do it. It's a bit like a magician. Going to pull a rabbit out of a hat. So I'm going to turn around this antenna now and point the Paradar Yagi down the test range in roughly the same place as the other antennas were, and I'm going to connect the cable, and again you won't be able to see this. Sorry about this. I could try editing my videos, but it's not supposed to look slick, and you've noticed that the music is very minimalistic on my videos, like no music. So there we are, that's connected now. The Paradar 8 element Yagi connected to the network spectrum analyzer. Now I'm getting minus 51 dBm. It can hang there. That seems to be okay. Sorry about the cable. Now I'm going to move around to find a peak again. Minus 50, minus 51. So it looks like it's about minus. I did do this earlier, of course, to check what's going to happen, and I got about minus 50 dBm. Let's call it minus 50 because it's close. And so you'll remember that the flat panel gave me minus 54. This is giving me minus 50, so that's about 4 dBs more. And I estimated the gain of this to be 8 dBi. If you add 4 dBs, you get 12, which is the claimed gain of this antenna, 12.5 dBi it's sold as. So these figures do seem to add up fairly well. I'm quite amazed actually because of all the reflections that are going on in this room and down that corridor. There I was minus 50, yeah, minus 50 dBm. Of course I'm standing here moving around, which is also affecting the measured signal results. But as you can see, this antenna is giving about 4 dBs gain more than this antenna, which looked like it was getting about 8 dBs gain maybe. So looks like this is 12 dBi gain, and the theoretical gain of this is 2 dBi, 2.1 dBi. So the numbers seem to be fairly close to the theoretical values that we would expect. So I'm happy, and I think the conclusion then is that the Paradar Yagi antenna probably has the higher gain, and the McGill Microwave flat antenna has less gain, which is what it is sold as. The big advantage, of course, is that when I walk up a hill one day when it stops raining to try some outdoor tests and measurements, it's a bit unwieldy carrying this or taking it on the bus and then walking up a hill. It's a bit tricky to carry, whereas this flat panel will just fit inside a rucksack because it's not much bigger than a laptop, so it'll go in the laptop slot in my rucksack, so it'll be easy to transport. So I'm looking forward to making some measurements in the not too distant future. So that's it for now. Hopefully you will have some comments to make and questions to ask and suggestions for next videos. I think the next video will be to measure the return loss, or SWR, from these two antennas to compare them and to see how that is, and I will upload that video shortly. Thank you for watching, and remember to like and subscribe, and see you in the next video.